Good afternoon, everyone. My name is Carl Mitroff, and I'm the AeroDef Conference Manager. Thank you for joining us today for SME's Technical Community and AeroDef Manufacturing Satellite Session. We appreciate the time you take out of your day to join us. But before we begin, I'd like to cover a few housekeeping items. First of all, you'll recognize that your microphones are automatically muted. If you have questions regarding webinar functionality, please use the chat feature. If you have technical questions that you would like to ask our speakers, you can submit them using the Q&A box. We'll be monitoring both. And in the event of any technical glitches that occur, please note that we are recording this presentation and we will make it available on the AeroDef website. Today's webinar, Advanced Composites Enabling Space Exploration for the Dream Chaser Cargo System, will cover the cargo system's capability and the use of advanced composites as an enabling technology for spaceship development and ultimately space exploration. Hosting today's webinar is Steve Parsons. Steve holds a position of Lockheed Martin Fellow Emeritus in the Manufacturing Technology Organization at Lockheed Martin Aeronautics in Marietta, Georgia. He has 35 years of experience in advanced manufacturing and assembly with a focus on composite bonded structure, automated fiber placement, and innovation composite manufacturing methods. Thank you, Steve, for moderating today, and I'll kick it off to you.
Thanks for the kind introduction. It's my pleasure to introduce Dr. Dan Polis, who is currently serving as the director of the Dream Chaser Cargo System spacecraft for Sierra Nevada Corporation based in Louisville, Colorado. In his role, he manages a team of engineers responsible for the design of the spacecraft for orbital flight, International Space Station service, re-entry, and reuse. Before joining Sierra Nevada Corporation, Dr. Polis spent 10 years at NASA's Goddard Space Flight Center in Greenbelt, Maryland. At NASA, he played an integral role in the development of several one-of-a-kind composite structures, including the composite crew module, the cryogenic composite metering structure on the James Webb Space Telescope, and the super lightweight interchangeable carrier for the delivery of the Hubble Space Telescope new instrument package to low Earth orbit on shuttle mission STS-125. So with that, I will turn it over to Dr. Polis.
Thanks, Steve. I want to make sure you guys can hear me. I see a network error popped up here on my windows. Everybody hear me okay?
Yes, I can hear you fine.
Yes,
great.
I hear you well, Steve.
Great, thanks. Well, it's a pleasure to be here. It's been about 10 years since I've done a webinar, and actually at that time, I was also talking about composites enabling space exploration, but for some of the missions that Steve mentioned. So now I'm happy to be able to share kind of what I've been working on for the last 8 years, the Dream Chaser cargo system, and a very, very different use of composites, but again, enabling some advanced technology and space exploration in a very unique way. So if you could go to the first chart. So the first several charts are a little bit about Sierra Nevada and what Sierra Nevada does. I think it's relevant. While I'll be talking about composites, I want to talk about some of the other technologies that go into the Dream Chaser. And for folks not familiar with Sierra Nevada, I thought it was relevant. So again, before I came out here 8 years ago, I didn't know much about Sierra Nevada. It's a privately held company by Fadi and Aaron Osman, shown to the upper right. We're a mid-sized company, only 4,000 employees, but trying to do big things like the Dream Chaser. So it's exciting to be a part of this company. But it's been around for a long time. So established in 1963, this isn't just a startup. We've been doing it for a long time. And so we kind of combine that heritage experience with kind of the small startup mentality. We've had some rapid growth that actually includes the Dream Chaser. So as I'll talk about later, the history of the Dream Chaser was through an acquisition of SpaceDev. And we've developed quite a reputation supplying the government, Air Force, NASA, as well as other branches of the government. And we're pretty proud of our reputation. We serve the government really through 4 business units: our ISR, Aviation and Security Division, our Integrated Mission Systems Division, our Electronic and Information Systems, and then the Space Systems Division that I'm part of. I want to go to the next chart. So again, no details here, but we serve not just defense and national security, space systems, but also commercial solutions. Next chart, please. So while we've been around for 50 years, our space division has been around only 25 years, but that's still a good amount of time to where we've gathered lots of successful product deliveries with no on-orbit failures, over 4,000, supporting 450 different missions, launching, every month, less than every month, supporting 70 plus NASA missions. But of course, the reason I'm here, what attracted me to come out here was our flagship programs, starting out and trying to provide crew services, now providing cargo services to ISS. Next chart, please. So our space division, as Steve mentioned, I'm in Louisville, Colorado. Our space exploration division is really headquartered there. But we have several other parts of the space systems group. Space technologies, they focus primarily on electrical power systems, precision motion and pointing control, separation systems. And then our RBI division primarily, although we do some propulsion in Louisville as well, out in Madison, develops propulsion systems, reaction control systems, nuclear power propulsion systems, as well as ECLS, or environmental control and life support systems, thermal control systems and radiators. So we do all kinds of stuff. I'm going to spend a little time talking specifics, and I'll start with space technologies. So if we can go to the next chart. So this highlights some of the detail work that we do in-house, some of which is critical for Dream Chaser. So for the launch adapter and separation systems, we use a clamp band separation system between our Dream Chaser and our cargo module. So that is developed in-house. Actually, it's been space qualified, and I'll point it out a little bit later. Moving to the right, docking and berthing systems. So the ring in the top right is the PCBM, or passive common berthing mechanism, that will allow us to berth to the International Space Station. That's developed in-house for our cargo system, and also we provide it to some of our competitors to dock to, to berth to the International Space Station. In the deployable structures world, we're not flying a truss structure like that on Dream Chaser, but we do have some complicated deployables, mainly our deployable wings, which is one of our most exciting kind of technology and implementation on the Dream Chaser. I'll highlight that in more detail. As well as, of course, deploying solar arrays, which fits into kind of the next two bins, electrical power systems and pointing and motion control, where we develop solar array systems and drive electronics to position those solar arrays. Moving over to flight and thrust vector control, and actually looking at the bottom, that's one of the actuators for control surfaces. And unlike standard aircraft, we're kind of in a very unique environment of very high power, high rate of our control surfaces. So it's been a unique challenge developing those in-house. And finally, thermal control devices. Next chart, please. In the propulsion world, of course, we're developing our own RCS system. Previously on the crewed version, we were developing our own abort system as well, but as I'll talk later, we no longer need abort capability for the cargo system. We develop environmental and life controls. Up top, you see one of our competitors that we provide components for in terms of ECLS, as well as developing our own Dream Chaser ECLS system. And then working I'm not, I have to be honest, not involved at all in some of the closed loop and bioproduction systems, but we participate in both the development and science payloads, science experiments for that area. Next chart, please. And then moving into the area that I work, space exploration systems. So of course, Dream Chaser to the left, you'll see at the top left there, our engineering test article, which was really created for kind of human spaceflight and crew services to station, and then how that's evolved to our cargo system. And then to the right, an area that we've been working heavily in is habitats and landing systems, and we've been awarded, we've had several awards recently to both do development and design work there. Next chart, please. So moving on to the spaceplane program. Next chart. I thought I like this history chart. It's interesting for me. This isn't necessarily a new idea that we came up with blank sheet, but really has its roots all the way back to the early 80s. So the pictures to the upper right were reconnaissance images from the Australian Air Force of the Bor 4 Russian orbital vehicle. That vehicle and those images serves as the foundation for the development of the HL-20, where NASA Langley spent a good amount of time and developed a lot of wind tunnel data, aerodynamic data, that was then translated by space dev to come up with the Dream Chaser concept in the early 2000s. Space dev was acquired by SNC, and so I alluded to that earlier. And then we started participating in a proposal for providing crew services. It started out with many providers and really got down to just 3. So in that, we won several awards, developed the design for the Dream Chaser, but also developed the hardware associated with our engineering test article shown to the right in 2013, where we performed our first drop test from about 10,000 feet and to demonstrate aerodynamic and handling quality of the Dream Chaser. In between the first flight and second flight, we pivoted and said, we could apply this concept to provide cargo services. I'll talk about the changes required to do that. But then in 2016, we were awarded that contract, the CRS-2, or Cargo Resupply 2 contract, as well as continuing to hit several key milestones like CDR, NASA awards, and our second ETA flight shown in 2017. Since that time, we've been developing both the design and building the ship. And so the primary structure arrived here in Louisville in 2019 with big help from our Lockheed Martin partners there for the manufacturing. And I don't have a date on here, but shortly after that, our primary structure for the cargo module arrived in Louisville as well. And we've been integrating the system ever since. First flight planned in 2022. Next chart, please. So this is our, I'll call it schematic of our Dream Chaser cargo system. And if you look to the left, I want to highlight really how we transitioned from human-rated vehicle to a cargo vehicle, and some of the key changes from at least part of the program that I manage. So things that made me happy, being, I guess, a materials guy by training and a structures person. When we got rid of crew, the astronauts could no longer say, we needed to look out windows. So that was the first thing we did, was reloft the front of the vehicle, get rid of windows, which were a very, significant technical challenge, obviously, to put, to survive re-entry, as well as, on-orbit pressurization and have the redundancy needed. We added a cargo module, so you can see the Dream Chaser atop the cargo module conic structure there. And we put ourselves under a fairing. The reason we did that, for human-rated flight, we needed to have an abort system. Once we went for cargo services, that abort system was no longer needed from a NASA requirements perspective. And so to decrease the aerodynamic load during ascent, we said, hey, let's fold the wings and go under a fairing. So that's really presented an interesting challenge. So folded wings, of course, are done on aircraft, but here we have to consider also the sealing requirements for our thermal protection system on reentry. So that has been quite an exciting challenge. If we move over to the cutaway view, ultimately this vehicle is the UPS truck that's bringing cargo back up to station and back. We provide both pressurized capability, so inside the Dream Chaser and inside the cargo module, we can provide up to 5,000 kilograms of pressurized cargo. And then located on the outside of the cargo module, we can provide up to 1,500 kilograms of unpressed cargo. And that unpressed cargo can take many forms. It can either have active release mechanisms on our side or on the NASA side, depending. Our total capability is 5,500 kilograms. So again, the balance based on what NASA really needs to get up to station, we have to balance that pressed and unpressed cargo. The cargo module is not just bringing stuff up, but it's also our service module providing power on orbit, as well as some other key capabilities. And then one thing, while both cargo module and Dream Chaser bring cargo up to station, on return, we'll separate the Dream Chaser from the cargo module. The Dream Chaser will have a low G landing on a runway to bring critical science payloads back, whereas the cargo module will burn up, essentially taking the trash from ISS on return. Next chart, please. So how do composites enable space exploration in the Dream Chaser? I put a chart, maybe because I like to think about where I was 10 years ago to where I am now. So I put a chart, next chart, on more traditional, especially since we're in the satellite session, on what I consider more traditional composite usage. Again, to the right is the Hubble super lightweight interchangeable carrier. That was my first introduction to composites. We didn't have enough capability in shuttle to take all the Hubble instruments that we wanted using traditional carriers at Goddard, and so this was developed to basically decrease the weight of the hand truck to bring better goods to Hubble. It used traditional, I'll say, satellite construction, and so I have the first bullet there, sandwich panels. They're used all the time. They've been used for 40, maybe 60 years on spacecraft bus structures, solar array substrates, optical benches, due to the high specific bending stiffness and low in-plane CTE. We took a similar construction approach on slick, but we did some pretty advanced things. Actually, the struts that you see to the lower right are actually titanium metal matrix struts. If you've ever worked with that, it's a 700 KSI compression capability. Pretty impressive. There's a hefty price tag that comes with it. But again, that slick construction used pretty standard aerospace type elements, sandwich panels, and then moved to the second bullet, struts and truss structures. Maybe I'll call it a more traditional truss structure for space, as shown in the lower right. That's where I spent the next several years at NASA developing the core element for the James Webb Space Telescope. So this had a survival temperature of 20 Kelvin. We actually used hybrid, basically mixed fibers to basically produce a 0 CT at the operating temperature of the telescope. And so we could really tailor that. We could dial that CTE in with the flexibility of composites by incorporating two fibers. Actually has a positive CTE until the operating temperature of the telescope, and then the slope turns negative. So at that tangent is really 0. And so that's pretty common. I wouldn't say that structure is common, which if you follow James Webb, you'll know almost every element of it is challenging. Exciting that it's going to be launching soon here. But metering structures are used all over the satellite world, as well as things like magnetometer booms. So when we're kind of re-entering to measure the magnetic fields of Earth, You really don't want a metallic structure nearby to interfere with the sensors, and so that's another common use of composites. Over at pressure vessels, of course, used in lots of places. There, the fiber is not used because of the high specific stiffness or low CTE, but we're using composites because of the high tensile capability. And again, the fiber is chosen accordingly, as well as the matrix for minimizing microcracking. Maybe most related to what we do on Dream Chaser is fairings. So fairings and some large launch structures. One of the benefits there, high bending stiffness obviously required during launch, but also part count reduction is one place where certainly folks have moved in that direction or been in that world for a long time. In the aircraft industry, I think rockets do the same thing. Next chart, please. So how have we used composites on Dream Chaser so far? So, I highlighted to the left in 2013, 2017, our engineering test article. It was a drop test article, so it wasn't meant to withstand re-entry temperatures. It wasn't as weight critical because the launch vehicle didn't have to carry it up and it didn't have full capability. But it used, again, composites because of the ability to quickly and affordably form a new complex shape. So again, we had a new loft for a vehicle. To create that in composites really is, I would say, speed-wise more competitive than trying to do that out of metallics, and that was really why we went in that direction. We also tried to use large format parts to reduce assembly costs. The other thing, I think, benefit that we see that came out of it was rapid development in that system because we used low temperature out of autoclave materials, which we couldn't use on flight, and also ease of repair. So we had some repairs to do between 2013 and 2017. Those were relatively straightforward to do and would have been more challenging on potentially on a metallic, at least for an orbital vehicle, metallic vehicle. We moved to 2020. So last year, I said the primary structures for both cargo module and Dream Chaser arrived to Taylor. So that's the floor here in Louisville. So those first benefits still stand, reducing the number of parts, forming complex new shapes. I guess I wouldn't necessarily say a conic is a complex new shape, but again, minimal tooling to form that, very few parts. If I look specifically at cargo module, it's constructed very differently than the Dream Chaser. So one thing we really needed to have a flexible secondary structure attachment scheme, and we chose sandwich construction. A lot of times you'll hear that it makes attachment very hard, but we use a scheme, a hard point essentially, that's very flexible that we can put in after and customize. This is a disposable item. Each mission will be unique. So without changing a lot of the underlying engineering, we can have flexible attachment scheme for every mission. It carries the primary launch loads, ascent loads. And so sandwich panel, again, that's where sandwich panel shines. And then we were really looking for an inexpensive one-time use application, right? This is going to be disposed of every time. But we actually traded early on a friction stir welded structure. And we're happy, you make decisions up front, but even in hindsight, this was a good one-off, or I should say, cost trade for us. Moving over to the Dream Chaser, probably the key technology that pushed us to this construction was the use of 3D woven joints for several reasons. First, we reduced part count and assembly costs. We reduced fastener penetration through critical elements. And we also needed really good durability. 15 missions, again, there's not much, certainly in the satellite world, there's not much reusability for spacecraft. As we're seeing for space exploration, there certainly is, and people pushing that envelope. We're certifying for 15 missions. We hope we could do more. We're on contract with NASA for at least 6. And then finally, a high bond line temperature. And I don't quantify that. I'll just say we're not at titanium, but we're much better than aluminum like shuttle for bond line temp. Next chart, please. So, I wanted to get into a few specific examples. I'm not going to present very much detail, but I'll show you some highlights on some of these technologies. So the first is kind of the part count reduction by going to these large tools. So to the left, you'll see up top, these are courtesy credit from Lockheed Martin and the folks down in Fort Worth for some great work on fabricating the primary structure for us. And that's the lower air shell, basically a 30-foot tool, serves as both a layup tool and part of an assembly tool. And then in the lower right, a tool that's almost as long, not quite, but much more complex in terms of its lofting, is at least one side of our upper air shell. And that lofting is very complicated. You may look at some of the lofting there and wonder, that doesn't look like an aero OML, but that's because we have to obviously offset for our thermal protection system. Again, on the shooting star, or as I usually refer to it, the cargo module, you can see from our friends out in San Diego, really two main tools for layup, a conic tool and a dome tool. So really reducing part count has kept costs down for that primary structure that we'll have to throw away each time. And both of that have been great partners there. Next chart, please. So this is the primary structure as it arrived, I think late October 2019 on the Taylor floor. So, a stat that we like, we normally don't use miles as units for building things, but we have nearly a quarter mile of 3D woven preformed joints in this assembly. Pretty impressive to be able to execute that. It integrates 150 parts into a single assembly. So I already alluded to some of our motivations. So some of the motivation here was to eliminate fasteners on orbit. Obviously, those are leak sources, and we have a pretty stringent leak requirement. So that was number one. We also wanted to eliminate penetrations through our lower air shell. They serve as kind of hot introduction points for re-entry, even though they're under TPS. We felt that was a worthwhile advantage. Certainly, there's a mass trade here on hardware versus 3D mass of fasteners and associated hardware versus mass of 3D woven joints. That trade was favorable for us. And then we believe the tooling situation was a net gain. And by that I mean, you can imagine for more traditional construction, every bulkhead and every ring frame would have a return flange on it, and the tooling becomes more complicated. And then the assembly to hold the tolerances on those return flanges can be problematic. Here we were able to eliminate that by having every frame and every bulkhead essentially made on a flat tool. Next chart. So this is some of the performance benefit that we get from going to 3D woven joints. Really, the top two, I think you could argue whether those metrics. You really care about mass, not necessarily part count, but I put that on there for reference. The manufacturing processes, I think that most people assume that a multi-step match drill is a simple operation. And while it is very well understood, very well known, there are many, many, many opportunities for non-conformances. And so again, the one-step Coban has its own unique challenges, but it eliminates, again, or it's really a trade here, and I think we're happy with that trade. The ultimate capability I normalized to, so this is essentially an equivalent weight study. So on the left is a metallic skin, metallic web, T-clip to metallic skin. The center is a composite skin to metallic web. And to the right is our 3D woven preformed joint. And the capability of the preformed joint is 2.4 times that metallic skin, metallic web at equivalent weight, and significantly above the composite skin metallic web. Probably the biggest benefit is when you look at fatigue capability. So we cycled each of these to 37% of their own ultimate capability. So again, the preform is being cycled much higher, but still to 37% of its ultimate load. And we basically go to run out versus the metallic. Now, this is probably more, or some people may think this is more relevant for aircraft, but actually during descent, the descent dynamics for us actually impart a lot of cycles. And so this was also a critical parameter for us to certify for many missions. Next chart, please. So coming from the satellite world, I had never heard the term, never considered the term compression after impact when dealing with composites, that we just don't design to those levels when we design truss structures or sandwich panels. And so we can really maximize the benefit of composites by designing to kind of pristine levels. When I moved into the world working on composite crew module and starting to really talk to aircraft folks, realizing that was something we absolutely had to consider, it started to really eat into some of the benefit of composites in terms of weight. And so here on the Dream Chaser, we really looked at trying to strike that balance. It's not an aircraft, right? It's not, people aren't throwing their luggage in it, but it's also not a satellite. And so we developed, you can see our little impact hammer portable here to the left schematic, and to the right is a qualification article. You can see some remnants there of the faceted front, where the front windows would go. This was from our crew days. And we really put this qual article through its paces. We put impact damage in acreage areas and joints, and then we cycled it to the most extreme conditions that the structure would see, and then we took it to design ultimate. And so this was a highly successful test, exceeding really what NASA required us to meet for a damage tolerance perspective, exceeding our life requirements. And ultimately, the final failure modes were also interesting. And I'll just say that bonded joints didn't factor into those final failure modes. Next chart. So this is some of our stiffness strength demonstration on the cargo module. So it's already been test verified to multiple launch provider ascent loads as well as ISS pressure requirements. The left picture shows kind of how we apply compression and bending to the structure. And then the right is actually a modal test. So this went through a proto qualification effort and successfully passed, and has also been model correlated. One of the things about reducing part counts, reducing joints, using bonded joints versus bolted joints is model correlation becomes, I'll say, easier. I won't say easy. And one of the examples on the previous qualification article that I showed, our first modal test of that, we correlated to less than with major modes within less than 3% without any model adjustment. So pretty impressive. A lot of that is because you don't have the joint stiffnesses are not as variable to dial in, and so that's been an advantage. Next chart, please. So one of the things that we learned at NASA was we needed, when we started working composite crew modules, hey, composites are leakier than metals. Of course, everybody knows that. But how well sealed do they need to be to meet kind of ISS requirements? And so we had started to look at this at NASA. And when we considered composites here, we actually took a two-prong approach. So for the right is the inside of the cargo module. And we went with a linerless construction there. We've demonstrated that we can meet the stringent requirements for a single mission. And so we can decrease the mass. But to the left on Dream Chaser, we're using a liner. And that liner, I won't get into the details, has to consider many things, but it's accounting for the fact that microcracking and impact damage can create leak paths that aren't accounted for when you do pristine testing. And so that is, I'll call it an insurance policy to make us very damage tolerant to leak. And I think that is my last chart, but next chart. And so with that, I think, Steve, we're going to open it to some questions.
Absolutely. I think that we see some on the box here. Can you see it, Dan, or do I need to read them to you?
I think you may need to read them to me.
How many re-entry missions are allowed before the external protective coatings need to be replaced?
Good question. Yeah, our thermal protection system is designed for 15 missions in most places. There are certain areas that use, I'll say, a less traditional thermal protection system that will be replaced each mission. But that's very, very localized hotspots where we need more extreme thermal protection. So it's really kind of 15 missions versus one. We try to limit how much PPS we need to replace for turnaround time.
So the next question is, do the co-bond joining operations occur in an autoclave, or do they employ out-of-autoclave prepregs?
Yep, they occur in an autoclave.
That's why we were able to help them, because we have a very large autoclave in our Fort Worth facility. Okay, here's another one. Are these technologies being used in commercial aircraft industry?
Yeah, well, I think I can't speak. I think qualitatively I can say yes, that these some of these are utilized. I can't really say more than that, and I don't have intimate knowledge exactly on how our technologies versus what's out commercially is used. Our implementation of this really came out of a push from going back as far as the Composite Affordability Initiative led by the Air Force, which and has developed significantly over time.
And I can speak to the market. Right now, most of it is co-cure. When you see these structures that are unitized, the co-bonding has not been able to pass the hurdle because of surface prep concerns with some of the customers. But that's being worked, and we continue to make headway on that topic. So at some point, hopefully we'll see that. The next one is, what is TPS?
TPS is thermal protection system. Essentially, it's our tile. So it's most of our tile is an evolution of the shuttle thermal protection system. But again, we have it's been advanced, as well as we have some unique areas that use a non-shuttle-like tile.
Here's one. What were the trades of the 3D woven skin stiffened versus co-bonded T-stringers like used in commercial aircraft?
So, we did weight trades initially for both, I'll say, weight trades for material as well as joining, as well as vehicle layout to come up with frame spacing. So again, we really were interested to get rid of, for instance, sandwich structure on the Dream Chaser due to reusability. And so we had to trade that with frame spacing. And we used some optimization programs to kind of do those high-level trades.
Okay, we got one here. This is, in the manufacturing processes, there's still work being done by humans, or is the process mostly automated, and if so, which tasks?
Yeah, so we that's a good question. So ours were still done by humans, both on the piece part fabrication as well as kind of the assembly fabrication. That was a conscious decision. Actually, we did do some automated fiber placement in certain areas during the development of this program. The one area that I think if we were higher volume, again, building a fleet of Dream Chasers, we would certainly look at automated fiber placement of our pressure vessel as a very good application, but we felt that it was not a good trade for us given the volume of Dream Chasers that we're building today.
Okay, here's one about the propulsion. How many missions until specific engine components need to be replaced?
Yeah, so our propulsion system is also designed for 15 missions. I don't think I can say too much more about where we are in the qualification, but we've just had some major qualification events completed.
This is from one of my good friends at Spirit Aerosystems. Were you able to inspect 100% of the bonded surface? Did you have to design using assumptions of undetected flaws?
Yep. So I would say we could not hit 100%, and we used various other methods to, I'll say, certify the structure, both non-destructive inspection as well as, well, I would say when you use the term non-destructive inspection, traditional ultrasonics and other methods, we didn't get 100%. We used some other methods to interrogate to get us comfortable, and then a variety of other things to close out the certification.
Then we got one on the TPS here. How many reentry missions are allowed before the external TPS coatings need to be replaced?
I think I answered that one already.
Okay, my bad. That we need to answer too. Okay, let me rerun these. I'm trying to figure out how they're stacking in here and coming in. That one. Let's see if I can find a new one. Here's a new one just popped in at the top. Let me go get that. I think this one's probably not. You're not going to be able to answer because it's about the composition of the TPS. So.
Yeah, I can't give any specifics really on the composite construction or any real details on any of the materials that we use.
Okay. Let's see. Yeah, one of the things that is an advantage to co-bonding, you get to inspect the details before you join them, so you don't try to bond together something that didn't pass NDI. We did use our laser ultrasonic inspection system in Fort Worth for a lot of the scan inspections and the web inspections. So, here we go. I'm looking to see if this one's another one that's talking about the manufacturing process. The actual manufacturing of the Dream Chaser itself and the processes involved it's an area of interest. Does SNC work with Industry 4.0 technologies such as AR? And that's augmented reality, I believe, is it?
For the fabrication of the Dream Chaser primary structure? Or I guess you're talking about integration of the vehicle. So we have used augmented reality to look at some critical installations on the vehicle. So again, when you're trying to figure out, can you get a tank into a large heavy tank into a very small place? We've used some instances of augmented reality, and we've also kind of used some old school methods of building a mock-up and mocking up kind of those installations.
There's one. What CAD tools do you use for the design and finite element analysis?
We use NX and BMAP Nastran.
Okay. 21 in the queue here. I'm going to try not to. There's a new one. This one's meant, so as you mentioned, the Lockheed Martin fabricated some of the components for you. Do you outsource all fab or some of it done in-house?
Good question. We have kind of built a pretty good supply chain network for composites. So I highlighted two of our partners, Lockheed Martin, as well as Applied Composites San Diego. We have many more as well. But we're actually installing a 10-foot diameter autoclave next month out in Louisville, so we can both build our own components as well as repair components as needed.
Okay. I'm not sure if I got this one. If I understand this, without a liner, how are leaks prevented? And I'm assuming that's a pressure vessel.
Yep.
Question.
Yep. So one of the things for composite leakage, it's obviously the reason it's worse than metallics is the permeability through the polymeric matrix is much lower than through a metallic material. So we can afford that hit. That in and of itself does not prevent us from meeting our leakage requirements. What we worry about more is kind of the linking up of I'll say microcracks. Those tend to form. It's a function of both the laminate thickness, the laminate layup, and is a function of thermal cycling. And so there, that's where we kind of separated in how we approach the problem for our cargo module, which doesn't see as extreme temperatures and has a different matrix system than our Dream Chaser. We were able to meet the requirements without a liner.
Yeah, and the other thing, that also was one of the factors in not using a out-of-autoclave material system because of the porosity that's a little bit higher in most of your out-of-autoclave systems. That kind of drove us into the autoclave solution for sure. And this one's about, can you talk about the solar panels?
I don't have probably enough detail that you'd be interested in. 6,000 watt solar panels, or 6,000 watt 3 panels. I don't really know. Can give too many details on the construction.
This is a question about the preforms, and I believe the answer is yes. So you might have mentioned this already, but is the 3D woven joint a pi preform?
Yeah, I can't really say.
Okay. Let's see. All right. If someone had a way around the third co-bond, could manufacture the whole third? Oh, I'm sorry. 3D co-bond. Could you manufacture the entire 3D structure without co-bonding, or would that be interesting? Is it tensile strength stronger with a co-bond? No,
I'm not sure I followed that question.
It may be a versus fastened structure. I'm not sure where that was going. If there's
so I would say the joining technology that we use really allows us to get to skin strains that are at or exceed the allowable, and that's really the critical piece. That we can react enough load through that joint that it's not really the rate limiter. Now that's not always the case. So again, I showed the raw primary structure coming in. We put a ton of metallics on, and where we have high load introduction, there's often fittings. So you didn't see that, right? And that's obviously, you have to know when you're looking at an acreage solution versus a point load introduction solution.
And this one is the laser ultrasound inspection. I'm not sure what this acronym, LBI or similar proprietary system, or is it COTS? It's a Lockheed Martin developed laser ultrasonic, and it emulates the Cscan from ultrasonic by imparting energy into the surface of the laminate, and we're measuring its response with another laser. So it has an excitation laser and a measurement laser, and it generates essentially a Cscan equivalent.
Yeah, rather than using a transducer, it uses kind of the heat generated at the surface to basically create the ultrasonic wave.
Yeah, and it does. It is almost a one-to-one comparison with a conventional Cscan on the kind of output you get. Okay, this one's here comes one. Let me see. What discriminators were used in the composite fiber resin selection for this application? Was it anything other than stiffness versus cost?
I think, we used a combination of, so again, we could go with various temperature capabilities that were needed, and what that, at least on the Dream Chaser, what that translates into is, if we have lower temperature capability, we have a thicker thermal protection system, which is added mass. And so we traded, looking at those types of things to say, and actually our bond line temperature at the time this decision was made long ago, is we had to come up with reasonable conservatism to make sure that the structure could handle some pretty extreme environments, and that set our structural OML. So that was probably the number one. The Dream Chaser bond line temperature was a critical decision that drove several things.
So this question is, the person is asking who would be the right contact for augmented reality and how that would work within Sierra Nevada. Is it you, Dan, or would you direct this person to someone else? I guess is where the question's headed.
Yeah, they can certainly reach out to me. I'm probably the best place to start.
Okay. Let's see. The one stone. It's nice when they put new ones in because they pop in at the top and it's easy to find them. You start getting stacked up. I think we've gotten maybe at least 80% of them we've answered. Oh, there's one. This one's going to be easy. I shouldn't have skipped over it. The question was, has the Dream Chaser launched yet? I think that was. I think you covered that one, but it may have been right at it may have been kind of a subtle explanation.
So Dream Chaser's first launch scheduled for 2022. So the pictures I showed of kind of Dream Chaser engineering test article flight were just from a drop test, very similar shuttle kind of verifying aerodynamic qualities, 10,000 feet and down to the runway.
This one's one you need to put on your mentor hat just for a minute, Dan. What advice would you give to an early to mid-career engineer who aspires to reach your level of success?
Well, I would say the most important thing is to have fun. So my first job was not in aerospace, was not in composites. I really wasn't having a fun time. I ended up going to NASA and started working on Hubble and Slick and fell in love with composite structures. And it never really felt like a job after that. So I think if you find that, you're going to be successful because you're going to be happy. And so if you don't have that, maybe ask yourself, the grass can be greener, I guess I would say. Don't stop at the first place you land necessarily. And again, I never thought I'd leave NASA, and here I am in Colorado at SNC, just kind of following what I love.
Great answer.
Yeah, great answer. And that's a great place kind of to wrap it up. We're kind of pushing into that 1 hour time frame, so I wanted to kind of step in and thank everyone for attending today. There was one question, however, that I wanted to kind of pose out that we talked about earlier, and if you're not comfortable, Dan, addressing, that's fine. But what was the most challenging design hurdle you had to clear with DCCS?
Yeah, so I think probably a lot of when you know the problem that you're solving, they're all solvable. I think the vehicle integration problem where let's say the primary structure is a long lead and we're trying to design it, but yet the propulsion system's far from complete. We had it's a gray area to try to decide what's good enough. We're going to go make the primary structure and everybody else is going to have to adjust. And those decisions are continually made during concurrent engineering, what's good enough. And I think that's where engineers struggle. It's not black and white, and navigating that gray area is still the hardest thing.
Good, thank you. Steve, any final words from you before I close it up? Or Dan, any final words from you?
This is a real easy one. I can even answer this question they asked: would this be an unmanned or manned mission? And of course, it's probably real early in the presentation to abandon this, but you switched from manned to cargo, so it's an unmanned.
Unmanned, yeah. And I guess Carl, I'll just say I want to thank SME for inviting me. I'm excited that I could be here to share kind of the Dream Chaser, which I think is a great program, and I'm excited to share it. So I hope it was educational or interesting for the folks attending. And thank you for hosting.
No, thank you all.
Thanks, Dan, for making a commitment to spend time with us and put this presentation together.
Sure.
Yes, thank you, everyone. What a great discussion, and I appreciate your time again. Thanks to Steve and Dan for providing your technical insights in advanced composites and for supporting the manufacturing community and SME. A very special thanks to all of our attendees who participated today. We're going to send out a quick survey, post-event survey, and we would really appreciate if you could spend a few minutes providing your feedback. Your feedback is critical for us to continue to provide content that's valuable for all. Just one more note: this webinar has been recorded, and it will be made available soon on our AeroDef webpage. And finally, want to quickly promote our March webinar, which is on March 18th at 3 o'clock, and we're going to present laser sintering of polymers, so a little bit into the 3D printing area, and registration for that webinar is currently open and live. So again, thanks everyone for their time and investment. Really appreciate your time and support, and have a great rest of your day. Thank you, everyone. Bye-bye.